Hello, and welcome to this example on propagation of error. So, as you'll recall from the earlier lectures on error, when we establish a confidence interval on a measurement, that is, we want to have some nominal measurement, which I'm going to just for now call x bar, plus or minus. We write a confidence interval in this form, and so this might be something like 5 inches plus or minus a quarter of an inch, right? So let's say very poor, right? So a well-stated measurement might look something like this, right? And of course, we were using the z tables to figure this out. But as we started talking about in propagation of error, right, like there are these more complicated situations that show up in real situations where the measurement is not made directly. It's calculated from a number of direct measurements. Now, I'm going to give you a more complicated example today, which is the rotameter. I love a good rotameter. They're just wonderful measurement devices. If you want to measure a gas flow rate, for example, so let's say you've got a tube with some flow rate of gas coming through it, and you feed this through a rotameter. And we also measure the pressure. Okay, so there are two in a rotameter. Rotameters are just delightful little devices. It takes a very complicated problem, which is how do I measure the flow rate of a gas, and it solves it just very elegantly. So you have this tube inside of the rotameter. When you look at a rotameter, there's a ball floating inside the tube. It just floats at a certain level, and wow. And the higher the ball floats, the higher the flow rate of gas. Well, how does that work? Well, the tube is made with a very precise taper. That is to say, it's wider at the top than it is at the bottom. So if I were to zoom in on that ball and draw it over here, what you would see is something that looks like this. In reality, the taper is very slight, and there is a tiny gap, this tiny little gap. And the gas is forced to go around the ball and through that gap. And when it does that, it creates lift on the ball. The accumulated pressure underneath the ball causes it to rise. Well, as the ball rises, that gap increases. It widens, right? And the flow rate through that gap relaxes. And what you find is that the pressure supporting the ball decreases. Well, the ball's weight is the same no matter what. So the ball has some downward weight, which is, of course, we know that one. Yeah, and of course, and then there's some lifting force. Now, we could get into how you model the lifting force. We could have a whole lecture on that. It would be fun, but that's not our purpose today. Our purpose today is to emphasize how you actually read a calibrated measurement for one of these delightful devices. So the higher the gas flow rate is, the higher the pressure drop across the ball, and so the higher the ball can rise before its weight is in equilibrium with the flow rate of the gas. And so what we find is that the height of the ball is linear with gas flow rate, and this is wonderful. Now, the one caveat is that the calibration for this device is pressure sensitive. So I might develop a calibration for a rotameter. So let's say Q dot is the volume flow rate. Oh, you know what? Let's not use Q dot. We use that for heat, right? So some people sometimes use Q for volume flow rate. I'm going to use V dot is, for a rotameter, is equal to some slope, we'll call it M, times height, which is going to be the measured height in millimeters, plus some offset. So we could, in a very precise device, measure the flow rate of gas here versus height, and what we would see is data forming a straight line with some offset here, B, and some slope, M, right? And so height would be of the ball would be meters or millimeters, whatever you want, and then volume flow could be in any units you want, cubic feet per hour, it could be in cubic or liters per minute, whatever you're working in, volume flow. So now there's let me give a little rant about the ways that rotometers are usually read. A lot of manufacturers, where do you measure the height of the ball? Like the ball has some thickness, and there's a graduation on the side of the rotometer, right? That tells you from which you read it. The best rotometers, in my humble opinion, are rotometers that have a millimeter graduation and allow you to construct your own calibration for them. But where on the ball do you take the reading? There are an alarming number of manufacturers that tell you to read the scale from the middle of the ball. These manufacturers make me want to set the building on fire, because you have chosen the hardest place on the ball to reliably find visually. The top of the ball is really easy to see. If I'm looking for a line that forms right on the top part of that ball, that is really easy to see. But the middle of the ball, I mean, you could squint and tilt your head and convince yourself that the middle of the ball is in this pretty wide range, right? That is the hardest part of the ball to read. It is the least reliable place to read. It is the hardest place to train an operator to reliably read. The top of the ball is absolutely the better place to read the ball. Okay, now that I've had that rant, anyone who tells you to read from the middle of the rotometer ball, be skeptical about their design capability. I fundamentally disagree with that as a philosophy for how to read a rotometer. Okay, anyway, so this is the calibration. What could possibly be simpler? Well, as it turns out, it's more complicated than that, because this calibration would be taken only at one pressure. What we find is the whole curve, as I change, so that might be at some initial pressure I'm going to call P naught. What we find is if we repeat this with the gas line at a different pressure, the whole curve shifts up and down with different pressures. Oh dear. Well, but this is actually this is something we can deal with. We have math. We know how to do math, so we can deal with this. If we did a physical model conducted a physical model for the performance of the rotometer, absent viscosity, here's what you would end up with. Is it turns out it goes like this. So assuming you developed the calibration for the rotometer at a certain pressure, P naught. So in our scenario here, we went to the lab and we calibrated our rotometer, and we've got a MN and a B value we really like in our gas at P naught. So let's say we're doing it in air. Fine. If it's a welding application, it's probably argon, maybe carbon dioxide. It could be a blend, but yeah. So you've done this, you've got it. Great. Well, then we want to adjust the pressure, but I don't want to have to go back and re-measure a calibration. It's okay. We can just adjust the entire calibration by this factor out front, and it'll be pretty darn solid. Okay, so terrific. That's great. But here's the problem. We now have two direct measurements. One is a pressure measurement from a pressure gauge, and the second is a height measurement from a millimeter graduation here. And as we've already established, there is some error induced just by reading the scale here. And if your manufacturer is one of the stupid ones that thinks that you should read from the middle of the ball, well, then you're stuck with this less precise method, which is really irritating. Okay. So we need to figure out, if we want to figure out a confidence interval on V dot, on the volume flow rate of gas, then we need to figure out how error propagates through this calibration from both my height and my pressure measurement. That's the challenge we need to solve in this example. Okay, so there's the background, and here's how we're going to do it. By the way, if you don't think that this is a realistic analysis, if you think I'm just making busy work, go down to the machine shop. Obviously, not right now, we're in the middle of a pandemic, but when you're able to, go back down to the machine shop and look at what's mounted on the gas cylinders for all the welding kits. There are flow meters, and this is how they work. So if you want to know how accurate they are, this is how you figure that out. Okay, and I guarantee you they did this analysis where they manufacture them. I know that because, well, the company I worked for, we manufactured them. Okay, so here we go. The calibration, again, looks like this. So presumably we've gone into the lab and done all of this. I actually did this when I worked at ESUB. I've calibrated quite a few rotameters. All right, so we get this. Presumably we have values for M, we have values for B, and we have values for P naught. So so what we have is a calibration of the form. The volume flow is a function of the height of the ball and the pressure in the rotameter, right? And so those are our two inputs, and we want to measure. So given if we have a certain amount of standard deviation or uncertainty in H, and if we had a certain amount of uncertainty or standard deviation in P, the question is, what would the standard deviation of V be? This is an interesting question. So what we learned last time, or what we learned in the lecture on propagation of error, is it's a sum of the individual variances, not standard deviations, variance due to each of these. And the way we do that is we say that the variance on volume flow is equal to, well, what is the variance due only to, we'll start with height. It's this, the partial derivative of V with respect to height squared times the variance of height plus the partial derivative of V with respect to P squared times the variance in P. There we go. So if we can just evaluate this equation, we'll have our new variance for volume flow. And this is how it's done. Okay, so let's start with taking the partial derivatives of this equation here. So when we start with height, we need this first. Remember, when we take the partial derivative with respect to height, we get to assume everything else in this formula is constant, right? Everything's constant. So my P's, even though they're separate inputs, the constant, M, B, constant, right? H is the only thing that changes. So this P over P naught out front just looks like a constant. And then when I take the inside derivative here, the answer is just M. That wasn't so bad. All right, let's underline that. We're going to need that later. Let's now calculate the partial derivative with respect to P. What is that? Well, now we need to differentiate out from here. This now appears like a constant, so it's not going to change. All right, I just need to bring this 1/2 down. P over P naught. This is now negative 1/2. And I need to multiply by the inside derivative, the derivative inside of this thing. Well, that's just 1 over P naught. Cool. And then I don't forget to multiply by this constant that's lagging behind, M, H plus B. It looks a little messy, but it's actually not bad at all. You could, if you wanted to rewrite this, you could rewrite this pretty easily as... I'm pretty sure, yeah, that you get, yeah, you do. This is an even easier way to write it. Notice that if I take this and divide by p and multiply by a half, right, you get this. So that should be what you get. Isn't that lovely? So it's an easier way. It's just an alternate, easier way to write it. Okay, but you didn't have to know that. That's just a trick I like to use to make the algebra easier later. You could use this, no problem, to evaluate it. Okay, so we've got that much. Now let's add some numbers, right? So let's go ahead and give this calibration some numbers. So normally I like to pull the class for numbers, right, to prove that I haven't prepared in advance the answer and we're really generating it on the fly. I'll just have to make them up myself. So for P0, let's assume we're operating at atmospheric conditions for the calibration. So let's start off, we'll work in PSI, why not? So at atmospheric pressure, we're at 14.7 psi-A. So that's 14.7 psi absolute. So we needed that. For my slope M, let's say we're working in crazy English units, which are common in the welding industry. We'll say that M is, I don't know, 20, no, that's a lot, that's pretty high. We'll cut that in half. We'll say 10 SCFH per millimeter. SCFH is standard cubic feet per hour. So SCFH is a standard flow rate unit. The word standard has special meaning. We'll talk about that later. That's a whole conversation about thermodynamics. We'll worry about that some other day. All right. B is the offset, so this needs to be in SCFH. So basically, when it reads 0 millimeters, what is the flow rate? Usually, there's some minimum flow required to lift the ball up off of its seat, right? And if it's below that flow, you don't get any motion. So that tends to cause this offset B. Let's say that's some slow background flow rate of maybe 20 SCFH. There we go. Okay. And then we also need nominal readings. So notice that this is actually going to be a function of what is the pressure at my current reading, what is the H. The sensitivity of these partial derivatives are actually functions of what is my current reading. This is an interesting observation. What it means is this flow meter has different sensitivities at different operating conditions. So it's not that simple. It's not one answer everywhere in its range of operation. Most real sensors act this way. They have different sensitivities at different portions of their operating range. So this is actually a pretty real world example. Okay, so let's assume we're operating at some elevated pressure now. Let's say we're operating way up at I don't know, 50 psi-A. It's not unreasonable, actually, even for, it's a little high for a welding application, not crazy for plasma though. And let's say height is, my measurement height is about, I don't know, maybe 40 millimeters, something like that. Okay. So we've got a set, so this is a pretty realistic situation. We have, so these were from our calibration. We went to the lab and we measured those. That created our calibration. And then here are our two direct measurements that we took in the lab. let's assume that we know that we've got about, I don't know, 1 psi of standard deviation. And let's assume we've got about a millimeter of standard deviation in our height. Let's just say that this is our inability to read the scale accurately, right? Creates about a millimeter of random error, right? Okay, so if that's the case, then we're ready to start plugging in. The very first thing I'm going to want to do is calibrate. Well, calculate what does my actual calibration predict, right? So for that, I just need to plug in. V dot is equal to. I'm just going to borrow from right here. P was, we said I'm at 50 psi divided by 14.7. I'm going to get lazy with my units. So that's a square root. M is, I said, was 10 SCFH per millimeter. And then that's going to be times 40 millimeters. Plus the offset was a 20 SCFH, just to get it off, just to get the ball to lift off of its seat. Okay, so we can evaluate that. Let me bring up my handy dandy Python terminal. So 50 divided by 14.7 is about 3.4. Square root is about 1.8. And then that's going to be times 420. So we have about 774 SCFH. I'm being super lazy about rounding. Yeah, I'm assuming we're not that accurate anyway. So it's a pretty high flow rate. So yeah, that's moving right along. But that's not crazy. You can obtain this. This is more flow than you would see on a single welding torch for sure, and it's more flow than you would see on a single plasma torch. But on an air system, for example, yeah, on a shop air system, oh yeah, you can easily get these kinds of flow rates. Okay, let's keep going. So we've got what we think our measurement is for V for volume flow. Now let's figure out what its variance is. So we said that the partial derivative of volume flow with respect to height was this, square root of pressure times m. So let's write that. All right, that's going to be square root of P times m. And so m was just 10. Okay, so let's see. We said 50 divided by, this term here was about 1.8, 1.84 in fact, times 10. So that should be 18.44. Now what are the units on this? Let's take just a moment and think about units. So our original equation was this. The partial derivative, so the sensitivity of volume flow with respect to height. So how much does volume flow change per change in height, right? So if I hold everything else the same and I just wiggle height around a little bit, how much does the volume flow change? Well, the guts of this parentheses are dimensionless. That's pressure per pressure. That goes away. So the units of this are exactly the same as m. And m ends up being flow per length per millimeter. Flow per millimeter. Absolutely, that's correct. So this ends up being SCFH per millimeter. Perfect. Got that? All right, let's now move on and calculate that for pressure. All right, so if I look at the partial derivative of volume flow with respect to pressure, the easier way to calculate this was this. But you can use the longer way if you want. It'll work just fine. Just increases the probability of a silly mistake. I like this method for obvious reasons. So that's 1/2. It's going to be 774 divided by pressure, which was 50, we said. So that should be the same as multiplying by 0.02, which should be about 15.48, I think is what I get by mental math. Now let's find out if I'm right. Look at that. 15.48. Now what are the units on this one? Volume flow for pressure. Volume flow per pressure. Yep, SCFH. Per PSI A. There we go. I think we're ready to calculate variance. So we said to calculate variance, we needed, to calculate the variance on flow rate, we need the partial derivative with respect to H. Got it. Partial derivative with respect to P. Got it. And our individual variances. Got it. We're good to go. Here we go. And remember, this is not standard deviation. Let me say that again. This is not standard deviation. This is variance. It's the square of standard deviation. The most common mistakes on these problems is to leave out the squares, right? So don't fall into that trap. All right, 18.44. There's nothing about this that's really especially difficult in terms of just practicing it, but the little details like that are where people really get tripped up. All right, and then we needed the variance for height. So the standard deviation was 1 millimeter, so the variance is, well, I should be consistent and either include or not include my units. I shouldn't be sloppy like that. Sorry. All right, and then so this is SCFH per millimeter, and then this is millimeters. And then we needed the partial derivative of V with respect to P, which was 15.488, or 48, excuse me. And then we said this was about 1 psi. So purely just by bad choosing of numbers, both of these are 1. The interesting thing about this analysis is actually it enables us to see where most of our error comes from. This is a really unusual case where just by the luck of the numbers, neither of these really dominates. These are both on about the same order of magnitude. Frequently what will happen is when you do this analysis, it will become obvious to you that one of these is tiny compared to the other, and so you can basically say, all right, this is already really accurate. I don't need to improve this one more, for example. And it makes it, as an engineer, it makes it really clear where you should spend your money, right? Which of these measurements is more important, right? What do you need to improve more if you want this to be a more precise, a more if you want to tighten up your confidence bands. That's a question worth asking, and this analysis makes it obvious. Okay, so let's do this. All right, so we need to calculate 18.44 squared is 340. I should just pretend I'm doing this as mental math. Oh yeah, clearly 18.44 squared is 340. All right, now 15.48 squared. Yeah, no way. I'm not doing that. Not in my head. All right, and that's 239.63. I'll just carry one decimal place. This was 230.0, as it turns out. And so total. In total, we have 239 plus 340 is 579.6. Cool. And that is SCFH squared. So the standard deviation then in flow rate is the square root of that. All right, right, so the last step to all of this, once we've figured out our standard deviation, now let's take stock of what we've just accomplished. We've said that I'm calculating a calibrated flow rate from variables that have some degree of randomness to them, right? They're measurements. I trust them pretty well, but they have some amount of randomness to them. And I want to predict how much uncertainty that's going to create in my measurement, right? So how much error do I believe that is going to create in my measurement that I care quite a bit about? And we've just done that. We figured that out. Now I want to emphasize this is those of us who use digital gauges, this is going on, this sort of calibration is going on quietly, secretly inside the digital gauge all the time. The horrifying fact of it is you're just ignorant of what the direct measurements are, you don't know what the calibrations are, and you do not know how to do this sensitivity analysis inside a proprietary gauge. This is one of the reasons I hate proprietary gauges, is you just don't know what matters. You don't know how good it is. You just have to trust the manufacturer to have provided you realistic uncertainty. It's every now and then it's just worth it to suffer through the exercise of making your own stuff. All right, so now let's give this with I don't know, let's say maybe a 95% confidence interval. How about that? Does that sound good? So just to do that, we're obviously going to need the z-tables. So let me bring up my z-tables here. All right, you can't see them, but yeah, at this point you've done this before. All right, so the 95% confidence interval is going to be my expected flow rate, which was 774, plus or minus. Now here we need it to be my standard deviation, which is 24.1, times whatever the z value is that corresponds to, well, 475, 0.475, or 1/2 of 0.95. So when I look up 0.475, I struggle to find it in this little tiny table. Here it is. 475 corresponds to 1.96. A z value of 1.96. There we go. Or that's our measurement. We're done. And we're 95% confident it's within about 50 SCFH of the right value-ish, right? 47 is about 50. Yeah, so that tells us how much confidence we have in this measurement. The answer is I am supremely confident of this digit. I'm not so sure about this one. I have no idea what this digit is, and the decimal place is irrelevant, right? Yeah, we might as well call it about 770-ish, right? This digit is meaningless. It's way down here in the noise. Okay, well, thanks for watching. I hope this was useful.